I guess we should begin at this point. Well, it's a great pleasure to introduce today's speaker, Chuck Horowitz from Indiana University. Chuck is a participant in our current workshop on exploring extreme matter in the era of multi-messenger astronomy, from the cosmos to quarks, where we're trying to see what we can learn about dense matter now and in the future from observations with gravitational wave and electromagnetic of neutron star mergers, all the way through to observations by NICER, the X-ray telescope on the International Space Station, which Cole Miller, who's sitting here, described this colloquium three weeks ago. Chuck received his PhD from Stanford University with Dirk Valechka. He spent his time there, as he remarked, backpacking in the Sierras, and so he feels very much at home in Aspen and loves to come here. He's been at Indiana, which unfortunately is landscape in 2+ epsilon dimensions since the late 80s. He works at the intersection of astrophysics and dense matter, from neutron star crusts to freezing white dwarfs. He's also been involved for many years in the PREX experiment to measure the neutron radius of the nucleus lead 208, which may have interesting implications for neutron stars, in particular their crusts. Today, he will talk on a somewhat different topic: supernova ignited by nuclear fission experiments, by nuclear fission explosions, sorry, a new and innovative mechanism for producing type 1a supernova, the standard candles of cosmology. So let us welcome Chuck.
So thanks so much, Gordon, and thanks very much for the chance to be here. Given the rich history, let me see if I can get rid of that. Okay, great. So I'm really honored to the chance to talk, given all the rich history, Aspen Center for Physics. Whoops. Hello. There we go. Want to talk. So first of all, welcome to the Aspen Primer. Los Alamos started with the Los Alamos Primer server. So why can't we have the Aspen Primer? I want to present some lectures. Some of the first lectures, as far as I know, on naturally occurring atomic bombs. Let me emphasize my excellent collaborators. Matt Kaplan is now at Illinois State. He was a student at Indiana University with me, and his thesis won the American Physical Society thesis award in nuclear physics. It was entitled Astromaterial Science. Also, Alex Dybel is at Indiana University. Great. So if I learn how to work this, let's start 2 billion years ago in Africa, a place that will become the uranium mine. There was a natural nuclear reactor, very rich uranium ore deposit in groundwater became critical and operated as a nuclear reactor, produced exotic isotopes that you see today. Today, the enrichment of uranium, so I'll say enrichment is the fraction of uranium that's the isotope U-235. Today, that's only 0.7%. 2 billion years ago, it was something like 3.5%. Uranium has a 700 million year half-life, so it's been decaying since then. So the enrichment was higher earlier in the history of the solar system. 3.5% happens to be a typical enrichment in a light water power reactor. And indeed, that enrichment is high enough for a natural nuclear reactor. This reactor was stable. If it becomes too hot, the water boils off. The water is the moderator, scattering neutrons off of protons, slows them down, and the fission cross-section for slow neutrons on uranium is very big. So if you don't have the moderator, it's not critical. So this was a stable reactor. Fortunately, a natural nuclear explosion, a natural atomic bomb, is probably impossible on Earth, but it might be possible in a star. And so that's what I want to talk about. What could you do with it? Oops. I want a big explosion. So a type 1A supernova, it's a giant explosion of a single star, can be as bright as a galaxy. Important distance indicators in cosmology. They've been used to discover the acceleration of the universe and dark energy. Despite the awarding of the 2011 Nobel Prize in Physics, what exactly are type 1A supernova? What are the progenitor systems that actually explode? How do they explode? We don't fully understand. There's a significant tension in Hubble constant values determined from supernova observations and other data. The lack of understanding of the type 1A mechanism and the progenitor systems makes it hard to theoretically rule out unexpected sources of systematic errors that could lead to bias in the extraction of Hubble constant or other cosmological parameters. Okay. Present models for type 1As involve white dwarfs, carbon oxygen white dwarfs in binary systems. The single degenerate model has a conventional star transferring matter to a white dwarf. It's thought when the white dwarf exceeds the Chandrasekhar mass, it eventually explodes. The double degenerate model has two white dwarfs. They radiate gravitational waves, spiral together, and somehow when they merge, they explode.
Chuck, I'm sorry to interrupt, but we're having some problem with the sound, and you need to stay close to your computer.
Thank you.
I'm sorry. Thank you.
Great. Is this better? Okay.
If you're not wearing a mic, then you're not going into the
Okay. Great.
I have auxiliary speakers, but they seem not to be working.
Oh, there's a microphone where you can hold on the wedge.
Does this help? Is this working?
That is working.
What's that?
Yeah.
Okay. So great. I hope people can hear. There are many open questions and problems with both of these mechanisms, such as there may not be enough progenitor systems to explain the type 1A grid. Great. So I'm going to propose a new mechanism. So instead of a binary system, we have an isolated white dwarf and a natural fission chain reaction when material in the white dwarf first starts to crystallize. I'll get to that. Ignites the carbon burning and produces the supernova. So single degenerate, double degenerate, and possible fission mechanism. Okay. I told you what I want to do with the bomb. How do you actually make a bomb? You need enriched uranium. As I said, it was 7.7% today. It's too low. However, when the solar system formed, fully 25% of the uranium was U-235. So the solar system was formed out of enriched uranium. So we don't need to enrich the uranium. We just have to use young uranium. So we want to use it before it decays. And then you have to chemically separate the uranium from all the impurities. And so we're going to do that when it crystallizes out of solution, when the white dwarf first starts to freeze. Okay, and the final step is to actually set the bomb off.
Very naive question. Some of us grew up thinking that whatever happens in stars and whatnot was hydrogen conversion to helium, which leads to everything. But you're emphasizing this uranium fission.
So
Repeat the question.
yes, a lot of the textbooks have nuclear fusion occurring in stars. I'm proposing maybe nuclear fission can happen in certain cases.
But what's dominant?
Most of the time it's fusion. So the sun is shining via fusion. Okay, and we'll get back to that in just a little bit. To actually set off the bomb, you have to rapidly assemble a supercritical mass. And I'll just say a little bit how this was done at Los Alamos, and then say how that might be done in a white dwarf. Okay, so we want to purify the uranium. Separation of the elements, said the 16th century physician, started at the beginning of all creation. He believed that chemical processes such as distillation, condensation, and precipitation seen in the alchemist's flask mirrored those in the cosmos. So even the biblical creation itself might be regarded as a chemical process. Philip Ball is much more lyrical than I. So what I want to do is not talk like this. I want to watch stars freeze. Okay? Watching the star freeze is a lot like watching paint dry, only much, much slower. Fortunately, there's a really excellent spacecraft for watching stars freeze, and this is Gaia. So Gaia has mapped 1 billion stars in the galaxy, and in particular, Gaia has measured parallaxes for a number of white dwarfs in the galaxy. Okay, so we can plot with the Gaia information an Hertzsprung-Russell diagram. We have luminosity up this way, temperature runs back this way. So hot is over here where they're blue, cold is red. And a white dwarf starts hot and bright. So it starts up here, and then it goes to being cold and dim. So for example, a 1.1 solar mass white dwarf follows this blue trajectory, but it doesn't follow it at a uniform rate because between these dashed lines, it's actually freezing. So the carbon and oxygen in the white dwarf is converting from a liquid to a solid. The latent heat of the transition delays the cooling of the white dwarf substantially, so that white dwarfs tend to pile up in here while they're cooling. So Gaia has clearly resolved this delay in cooling from the latent heat of crystallization. Okay, and so this motivates studying in detail how material in a white dwarf freezes. Gaia gave me scientific license to study crystallization of higher Z impurities in a white dwarf. Whoops.
How long do they stay in that point then?
It can be a gigayear.
Repeat the question.
So the cooling delay from crystallization can be 1 billion years. Okay. White dwarf chemistry. At high densities, atoms are completely ionized. The electrons are gone into a degenerate relativistic Fermi gas. Most of chemistry is closed electron shells, and all the electrons are gone. So the chemistry, the normal chemistry is gone, and it's replaced by an interesting kind of classical chemistry. The nuclei form a Coulomb plasma, and the plasma can form a Coulomb lattice. The melting temperature of that lattice actually scales with the atomic number Z to the 5/3 power. So the melting temperature of pure uranium is 95 times higher than the melting temperature of carbon. So the very first solids that form as a white dwarf cools are greatly enriched in the actinides because those elements have the highest Z. Okay, and I want to show the composition, and this is based on a simple linear free energy mixing model. And basically what's going on is a competition between the entropy of mixing. So the uranium has a very low concentration in the liquid, so there's a huge entropy of mixing. And then there's a huge lattice energy. You're way below the melting temperature of pure uranium. So the uranium would really like to be in the solid. And so it's just a competition between those two. Okay, so this is an outrageously complete chemical composition. I have literally considered all 92 chemical elements. Okay, so abundance is here. Chemical element is this way. The black is the composition of the liquid. So hydrogen and helium, main sequence star burns hydrogen to helium. A red giant converts the helium into carbon and oxygen. And so the star is assumed to be primarily a 50-50 mixture of carbon and oxygen. So that's the black points way up there. That's most of the material. This stuff here is solar abundance. So I've assumed that this white dwarf formed out of material with similar abundances to the sun. And so these are the measured abundances of all the other elements in the sun. So iron 56 is the most bound nucleus. So it has a relatively high abundance up here. But in general, as you go out to higher Z, the abundance is falling off by 10 or 11 orders of magnitude. Okay, so I've taken the sun's abundances, imagine that all the hydrogen and helium is converted into carbon and oxygen, and then that's the black curve. And in particular down here, there's a fair amount of lead, and then finally that's thorium and uranium, and those are actually the guys I'm interested in. Okay, so that's the composition of the liquid. Most of this is based from detailed solar spectra and meteorite abundances. Okay, and in this simple linear mixing model, the composition of the solid that's in equilibrium is shown in red, and the lattice energy really favors high Z, and so the solid is made of uranium, thorium, and lead. So lead with a Z of 82, that's significantly less than 92 from uranium, but there's a lot of lead. There's 100 times more lead in the liquid than uranium. So actually we think that there's a significant amount of lead in the solid. Okay, so that's the sun's abundance, or the white dwarf's abundance, and when it freezes, suddenly the uranium is highly concentrated. Okay, so we've got a solid that's uranium, thorium, and lead, there may be some carbon and oxygen. For simplicity, let me ignore the carbon and oxygen for a moment. And you can ask, would a material like that support a fission chain reaction? So if a neutron caused uranium 235 to fission, that's the fission cross-section. F5 is the enrichment, that's the abundance of the 235 isotope. When uranium fissions, it emits new neutrons, that's 2.5 or so neutrons. And the fact that that's bigger than 1 is why you can have a chain reaction. So the numerator is the source of neutrons. You can absorb neutrons on all the materials present. And if this ratio is greater than 1, a fission chain reaction is possible. And to get that ratio bigger than 1, we find you need an enrichment of 12% or so, or larger. Okay, so if the uranium, when the star finally starts to freeze, is 12% enriched or better, you could have a chain reaction. And just try to keep track of everything. Let's follow the uranium. Uranium is synthesized in our process, nucleosynthesis, could be a neutron star merger, like what? Maybe. Where's my cursor? Whoops. Oh, now I'm hopeless. Great. Okay, so you synthesized uranium in an R process event. So when two neutron stars, for example, collide, they eject material, and that material can make uranium. That enriched some pre-stellar nebulae. A star formed. There was a main sequence lifetime. The star became a giant. Typically, you lose a bunch of mass at that point. And then became a white dwarf. The white dwarf started to cool, and then finally, the white dwarf first started to crystallize. And at this point, if the uranium is still enriched enough, you could have a fission chain reaction. So that's my scenario. And this just shows how long it takes to do these steps as a function of the mass of the white dwarf. And the short answer is that you need massive white dwarfs, around 0.9 to something like 1.05 solar masses. Lower mass white dwarfs take too long to do all this. So this mechanism probably explodes relatively high mass white dwarfs. Okay, so I want to set the bomb off now. So first, how do you do that? How was that done at Los Alamos? So this is the uranium bomb dropped on Hiroshima. You have one piece of uranium, another piece of uranium. This first piece was shot in a gun at 1,000 feet per second. It moved the last foot to merge with the second piece. So the bomb was assembled in, if you're going 1,000 feet per second, you move a foot in a millisecond. So the assembly time was about a millisecond. The bomb had 50 kilograms of U-235, about 10 kilograms of U-238. And actually, it's the U-238 that has a larger rate for spontaneous fission. So the rate of spontaneous fission in 10 kilograms of uranium is about 100 per second. So the time between spontaneous fissions is something like 0.01 seconds. You assembled the bomb in a millisecond, which is less than that. So the chance of pre-detonation is small. Okay, so we have an assembly time and then a background rate. You just want to compare the two. Okay? And so I'm going to do that for the white dwarf. The white dwarf is much denser, and density is really crucial. And the simple way to see the crucial density is to look at the plutonium bomb. So this is Fat Man dropped on Nagasaki. The plutonium core here, surrounded by a large amount of very carefully engineered conventional high explosives. And the high explosives imploded it and increased the density. So let's look at how things scale with density. A critical mass, you have a critical size for the bomb. The size is of order the neutron mean free path. If you're much less than the neutron mean free path, then all the neutrons will just escape. So you have a volume lambda cubed times the density. That's the critical mass. The mean free path is some cross section over the density. So the important thing is the mean free path goes down as you increase the density, and therefore the critical mass scales like 1 over the density squared. So you can take a subcritical system, compress it, and it becomes supercritical, and that's how implosion works. Great. Los Alamos really worked hard for a factor of a few in the density. What happens if you have a factor of 1 million or more in the density? So a white dwarf does implosion in space, where at much higher densities. So here's just a little table. The critical mass is of order 10 kilograms for a little boy. For the white dwarf, it's actually less than 10 to the minus 6 grams. Okay? And so that's just because the white dwarf is really dense. So you don't need a very big bomb at all because the neutron mean free path is incredibly short. Okay? If you have 10-ish kilograms of uranium, well, you get spontaneous fissions 100 per second. If you only have 10 to the minus 6 grams, you actually go a few years between fissions. So the background rate is low just because the mass is low. Okay? You have a gun that assembled in a millisecond. We believe the cooling white dwarf wants a crystal nucleates. That crystal can grow to 10 to the minus 6 grams in about 30 seconds. Simple estimate based on some known diffusion coefficients. And you can assemble very much faster than the background neutron. Okay? So it's easy to assemble a bomb if you work at high density. And in fact, when you get to 10 to the minus 6 grams, nothing happens because it's going to be a year before there's a first spontaneous fission. So the crystal keeps growing, and we think it grows to something like 5 milligrams, 1,000 or 5,000 critical masses before a neutron finally gets it. Okay. So what was hard and required implosion at Los Alamos is really easy in the white dwarf. So that's how you set the bomb off. Okay, great. So where are we? A fission chain reaction. And one more thing I should say. The electrons are highly degenerate. The pressure depends on the electron density. It doesn't depend very much on the temperature. And in fact, the fission chain reaction makes the system a lot hotter, but it only reduces the density maybe 25% or something like that. So degenerate systems, you can increase the temperature a lot before the system starts to disassemble. So the degenerate system will not disassemble. A conventional atomic bomb blows itself apart incredibly rapidly. In a white dwarf, you don't disassemble, and there's nothing left to do but just burn till you run out of uranium. So the system may become hot enough to ignite carbon fusion. This carbon burning, technically it's a deflagration like a forest fire that may later convert into a detonation with a shock wave. Don't worry about the details, which are not well known at this point. The idea is this could destroy the star and produce a diplomatic supernova. If you want to keep track of the explosive yield, the fission primary explodes with about 50 kilograms TNT equivalent energy. It's about 1/1,000,000th of the Hiroshima bomb, just because it's so small. Okay. The fusion secondary, it has a larger yield, 10 to the 29 megatons. Okay, where does that leave us? It leaves us with many open questions. What really is the composition of the first solids when the star very first begins to freeze? Is the uranium in the solid concentrated enough to become critical, or there are too many impurities that absorb too many neutrons? If a fission chain reaction does occur, can it actually ignite the carbon and produce a supernova? And if the carbon is ignited, what does that explosion look like? And then finally, how does this compare to observations? Okay, great. So let's take stock of where we are. The single degenerate mechanism has a companion star, and one can look for the companion star. So we'll talk about that. The double degenerate, where the white dwarfs merge, there are gravitational waves, and so one can look for the gravitational waves. I'll get to that. Our mechanism, you have an isolated star, and if you like, it's just blue. Okay, so if there's nothing around, maybe it's the fission mechanism. Whoops, well, don't worry about that. So let's think about the companion star. Simulations show that the companion star is expected to survive the explosion of its companion white dwarf. The envelope may get stripped. It may get kicked to a high velocity, but it should still be there. So this is a Hubble image of a supernova remnant in the Large Magellanic Cloud. This remnant was from an explosion about 500 years ago. If you take the most extreme kick velocity possible, in 500 years, that companion star should still be inside that white circle. No companion star is visible, and these authors claim this rules out all published single degenerate mechanisms, at least for this supernova explosion. Okay, so at this point, could be a merger of two white dwarfs, or maybe a single white dwarf ignited by nuclear fission. So let me talk about the gravitational waves for the white dwarf merger. Unfortunately, white dwarfs are too big and merge too slowly for LIGO or Virgo. Ground-based gravitational wave detectors are not very sensitive below about 20 hertz. And so white dwarfs are too big, they merge before the gravitational waves they radiate get to 20 hertz. So we can't observe white dwarfs yet. Space-based gravitational wave detectors, such as LISA, laser interferometer space antenna, planned for the early 2030s, should easily detect gravitational waves from binary white dwarfs and be able to characterize the populations of merging white dwarfs. so we'll have much more information about which white dwarfs are actually emerging. Okay, great. And so maybe the thing to do is to emphasize again, Matt Kaplan and Alex Seibel. I thank you guys very much for your attention. I really look forward to questions and comments. So I'll stop there. Thanks very much.
Thank you very much, Chuck. I open questions now. First question back.
Naive question, why uranium? Is there no plutonium in stars?
Plutonium.
Could you repeat the question, please, for the?
Why uranium? What about plutonium? Plutonium has a half-life of 20,000 years. That UCLA natural reactor may have bred some plutonium, just like the reactors in Stanford did. That plutonium then decayed to 20,000 years. In 20,000 years, interesting. Plutonium-239 decays to uranium-235. So if you're patient, plutonium provides more uranium.
In the abundance chart that you've shown, it says that the composition of the solid phase and liquid phase are different. So does it mean that on cooling, some part of the matter just it evaporates?
So some things.
Repeat the question, please.
Let me go back if I may.
Repeat the question.
So the question is, how come the compositions of the liquid and solid are different? Where did the extra material go? And so in this case, this is the very first solids. So the picture is the uranium precipitates out of the carbon oxygen liquid first. So you get a very uranium-rich solid, very tiny amount, and then the liquid is slightly poor in uranium.
So these are central densities then.
So this is assumed to happen near the center of the white dwarf because that's where it freezes first.
Okay. Cole?
That's a very creative idea, Chuck. A question about this is, when you think about normal thermonuclear burst mechanisms, one of the key considerations is cooling. If you have a temperature perturbation, does it cool off more rapidly than the generation density increases? If you look into that, and can that condition be satisfied here?
So yes, and I
Repeat.
think so. So he says, what about cooling? And let me give you a first part of the answer. The real answer is atomic bombs are incredibly fast, and high density bombs are even much faster than normal atomic bombs. So let me explain that. The thing you're worried about, the thermal conductivity of this high density electron gas is really high. So a lot of energy is taken away quickly by the electrons, and they're nearly degenerate, so they have long mean-free paths. Okay. But the chain reaction, it takes an incredibly short amount of time, like 10 to the minus 14 seconds, for a neutron to go from one fission to the next fission because the mean-free path is so short. So the neutron generation time is incredibly short in this bomb. So the fission heating rises incredibly fast. There's a group doing this simulation right now in Florida State, and their first preliminary results are that the fission is about 1,000 times faster than the thermal conductivity, and neutrino losses are slower still.
Sanjay.
So I have a question about how the uranium survives the main sequence evolution of the star. It's in a plasma with KV photons and MEV neutrinos. Do all of those processes not destroy the uranium?
So this is actually fine and been looked at.
Question, repeat.
So the question is, what about photofission in the main sequence star, destroying the uranium? People looked at this because it would be a source of antineutrinos from the sun rather than neutrinos. And I think all the rates of photofission are just incredibly small.
Sasha?
I have a couple. One is, do you know if there are any other natural reactors other than UCLA that are on Earth?
I don't know. I think that's a really good question. And UCLA is special because
What was the question?
are there other natural reactors? UCLA is special because it was so stable in the 2 billion years since then.
And another one is, usually exactly when this thing sets off, right, like mechanically, you know, like this thing falls apart, and you're saying in the star, right, when you consider it as just a, I guess I don't understand what it, once it sets over the core, what maintains this integrity and stability of the star itself? Is there a criteria? Is there a reason why it stays?
Yes, so the white dwarf,
Repeat the question.
what's the stability of the white dwarf and the stability of the crystal as it explodes? And so the center of the white dwarf, gravity is holding it in. It has a high density and high pressure. Very small uranium crystal. The fission reactions are going on really fast inside. For that crystal to disassemble, it can't raise the pressure enough to expand the electron gas. The only way it can disassemble is to diffuse into the carbon oxygen liquid, and diffusion is really slow.
Chandra, did you have a question?
Is there another axis here, which is the time?
Yes. Good question.
Repeat the question.
Could you just
Repeat the question.
So he's asking, what about time? And I should let you finish. Time for the chemical separation or for the star's evolution?
you have drawn this abundance as a function of V, and I wanted to know what was the time here and how it evolved to that, or how it will evolve.
Yeah. So my picture of the time, I'm interested in when the very first solids form in the star. So you have this huge interior of a white dwarf. It's a really good liquid. As it cools slowly over a giga year, at some point, the first solid will nucleate, and that very first, or nearly first, crystal is going to be uranium rich, I think.
Are there people who are watching online who want to ask questions? So I can't see that from here. Okay. Then Cyrus?
So in terms of biasing the cosmic acceleration measurements, I mean, the mechanism would be changing metallicity over time, or
Changing enrichment over time. And this,
What was the question?
the question is, how could this possibly bias cosmological measurements? And let me emphasize that the short answer is I don't know, and I'm not claiming anything at this point. But this mechanism depends crucially on the uranium enrichment, and that varies with time, varies with galactic age. So there's potential for mischief with this mechanism, but we'll see. There's a lot that has to be explored first.
so what happens to the stars below these two red dash lines in the Gaia's?
Repeat the question.
Yeah, so the Gaia picture
What was the question?
had a star. So the question is, I apologize, what happens to the star after it goes through the two dashed lines when it was crystallized? And the answer is it's the solid star. It's a white dwarf that's a crystal, and it sits there. And they don't detonate. Oh, a few of them, if I'm right, they detonate, but only a relatively small mass range with enriched enough in uranium. You don't need, so the binary models of white dwarfs have a really hard time finding enough binary systems to explain the supernova ring. But there are a lot of single white dwarfs, and it's relatively easy for this mechanism to explain the ring, even using just a small fraction of white dwarfs.
Let me ask, why do you need crystallization? Won't ordinary sedimentation do the job of increasing density?
Yes, if it happened fast enough. So there is diffusion. Uranium is heavy. It has a higher neutron to proton ratio than carbon. So it sinks slowly.
But you need the increase in density in abundance.
We need the concentration.
You
You have
need-
to increase the concentration.
Yeah, so why does that require crystallization?
It requires phase separation.
Yeah, but why crystallization?
Because we know that crystallization occurs.
So
The short answer is it doesn't require it,
okay,
but we think this phase transition is present.
okay. Further questions from the audience, comments, queries? Any people online?
We have a hand raised online from Andreas, if Andreas wants to unmute himself.
Thank you very much for a nice talk. And thank you very much for bringing in new ideas into this long debate on the progenitor of type 1a supernovae. So I've got two questions for you. The first one is related to the plot you showed for the cooling tracks of white dwarfs with the Gaia instrument. There you can clearly see that the white dwarfs are heading off towards this crystallization track. And my question is, could you use that to determine how many white dwarfs are on this track and what the supernova rate from exploding single white dwarfs would be?
Yes, so if you assume a standard initial mass function for star formation, a very tiny range of white dwarf masses can be comparable to all stars 8 solar masses and above, and that's the regime that's thought to give you quark collapse supernova. So a relatively small range of masses exploding this way can explain the observed type 1a rate.
Okay, and my second question is related to the spectral signature of the fission fragments. Your model has all the actinides and the fission fragments in the center of the white dwarf that's then exploding. Wouldn't we be able to see the fission fragments or uranium in the supernova at some point as a narrow line in the center of the supernova rest frame?
You're looking for 5 milligrams in a solar mass. Okay?
Okay, yeah.
The needle in a haystack doesn't begin to describe it. Yeah, the fission explosion was 50 kilograms of TNT in a whole star. So there's nothing left to observe this match after it was lit. And indeed, if it doesn't ignite the carbon, it has no effect.
Thank you.
Thank you, too. Further questions, online, offline? Or not? If not, let's thank Chuck very much for a wonderful and innovative idea. I remind you, there is wine and cheese outdoors, and for those online, there's virtual wine and cheese as well. Thank you. Thank you. Can I get a couple of your slides?
Yes.